Now let's look at the review assignment for Chapter 9. Question 1 here says, an opinion poll asks a random sample of adults whether they favor banning ownership of handguns by private citizens. A commentator believes that more than half of all the adults favor such a ban. The null and alternative hypothesis you would use to test this claim are. So in this case, when you first look at the examples or the possible answers, we know automatically it can't be A. You never write a hypothesis using statistics, you only use parameters. So for parameters, that would either be P or it would be mu if it was a means. This is obviously of proportions, and it says here the commentator believes that more than half of the bans. So H sub A is what we think is really the case. So we think it's more than half for that, so it would either be this choice or really that's it. So just by default, the alternative hypothesis tells us it would have to be letter B in this case. Be careful with choice E. Never ever should the null hypothesis be an inequality symbol. The null hypothesis is always an equal sign, and again, using a population parameter. Number 2, you are thinking of conducting a one-sample t-test about a population mean using mu, a 0.05 significance level. You suspect that the distribution of the population is not normal and may be moderately skewed. Which of the following statements is correct? Now, for letter A, it says you do not carry out the test because the population does not have a normal distribution. That is not necessarily true. We know that if the population is normal in the situation, we're fine. If it's not, then we need to either check the central limit theorem because this is a means, or if it's less than 30, then we have to graph it out and look for strong skewness and possible outliers. Letter D in this case is also not an option. It says you can carry out the test only if the population standard deviation is known. In this case, if the population standard deviation is known, which is sigma sub x, then what you would use for this test would be a z-test. Now, if we don't know it, we know the only difference is instead of doing a z-test, what we would actually do is a t-test. So that's not going to be a problem for it at all. Letter C is not going to work in this case. You can safely carry out the test if there are no outliers. True, if there's no strong outliers. It says regardless of the shape. We do still have to graph it out and look for any strong skewness, so the shape does matter in that case. Letter E in here is also not going to work. The T procedures, again, we already talked about when you would use them. That's when you have to do S sub x because you do not know sigma sub x. It says they are robust. You can use them anytime you want. Actually, what this means is because they are robust, though, you still have to test the conditions because if you use the T procedures, you have to check for the actual shape, again, by graphing it out. So even by default for here, the correct answer is going to be B in this case. You can safely carry out the test if your sample size is large and there are no outliers. I know this answer is a little wishy-washy in that we don't know what large means in this case, but they're kind of getting at, if you look at the other choices, clearly B is going to be the best answer. Again, we know no outliers is going to hold for smaller sample sizes, and large is going to be more related to the central limit theorem. Number 3, to determine the reliability of experts who interpret lie detector tests in criminal investigations, a random sample of 280 such cases was studied. The results were as seen here. So the examiner's decision if they were innocent or guilty, and the suspect's true status in terms of innocent or guilt. Here's the question. If the hypotheses are H sub O, a suspect is innocent, versus H sub A, our suspect is guilty, then we could estimate the probability that experts who interpret lie detector tests will make a type 2 error as what? So let's refresh what a type 2 error is. Remember, one way to define the type 2 error would be to say it's a failure to reject given that H sub O was false. Now, if you look at it in terms of that, H sub O is false. Well, H sub O is that you're innocent. So the true response would be if H sub O is false, that would mean the person was actually guilty. So in this case, we are looking out of the entire group of the 140 people. Now, of those, are we talking about the 15 or the 125? If in this case, we're going to basically fail to reject, so if we fail to reject it, then we're going to come back and say We can't go for guilty. We would have to say innocent, so they actually mean the 15 in this case. So it is the 15 out of 140 is the actual correct answer for this. Now this can be a tricky question, so let me break it out in a different way. Again, type 2 error, you fail to reject given that H sub O is false. So the first thing, H sub O being false, well, H sub O is innocent, so that's false. So that hopefully by default makes you understand this is H sub O being false, because this right here is H sub O. We think that they're innocent. And because we failed to reject, if we fail to reject means we cannot conclude H sub A, we have to stick with the H sub O, which technically we never conclude H sub O, but in this case, H sub O of what's left would be the 15. And that would be the probability for the type 2 error in this case. Number 4, a significance test allows you to reject a null hypothesis H sub O in favor of an alternative hypothesis H sub A at a 5% significance level. What can you say about the significance at the 1% level? I think it first helps to actually do a visual sketch of it. So here if we have our normal, approximately normal curve, our 5% significance would be anything lower here, and our 1% would be embedded in there. What can you say? Letter A, H sub O can be rejected at the 1% significance level. Well, first of all, let's talk about the rejection, right? If P is less than alpha, then we would go to the next step of rejection. And it says here, we were able to reject the null hypothesis at the 5%. So it meant that the probability is going to be less than this alpha value at the 5%. Are we guaranteed the probability is going to be something less than this 1% that is shown here? For part A, we're not, because what if the probability fell in between the 0.01 and the 0.05? Then A would not be true, so there, from that we could cross off A. Looking at B, there is insufficient evidence to reject H sub O at the 1% level. Well, I don't really know that either, because the problem is, because we were able to reject at the 5%, again, our probability was therefore in this range, there is sufficient evidence. I don't know. Again, if the probability fell in here, I could reject. If the probability wasn't here, I could not reject at the 1%. So this one, there's really almost like not enough information for me to clarify the response. Letter C, there is sufficient evidence to accept H sub O at the 1% significance level. Well, first of all, the big problem here, never ever would you accept H sub O. So that right there is a huge flaw. Cross it off just for that alone. Letter D, H sub A can be rejected at the 1% significance level. Again, this is just poorly said. You never reject H sub A. You reject H sub O and conclude H sub A. So this is poorly said. It's not accurately done. It can't be that because of that reason. Therefore, by default, the answer cannot be determined, which hopefully makes sense because, as I said before, we don't know if the probability is going to fall in this range or if it falls in this extra little bit of tail. Number 5, a random sample of 100 likely voters in a small city produced 59 voters in the favor of candidate A. The observed value of the test statistic for testing the null hypothesis was H sub O, P is equal to 0.05, versus the alternative hypothesis, H sub A, P is greater than 0.05. Now think about the test statistic at first. If you look at these options, does Z or T make sense? Now this is dealing with proportions. Proportions always uses a Z test. So from that alone, we can automatically cross off option E. It cannot be a T statistic. So then go back if you need to on your formula sheet for the test. If you look at the formula for this, it's going to be P hat minus P sub naught divided by the square root of P naught times 1 minus P naught over the square root of n. Based on that, we should be able to see the connection. The correct answer here is going to be B. Just be careful with it. The P hat actually comes from our sample, so 59 out of 100, so that's why we have 0.59 there. The P naught is going to be the 50%, and then again the P naught over here over our sample size. Just be careful with really the order of these other statistics. This is a very common type of question where they're going to test your ability to realize what values specifically go in the test statistic components. Number 6, a researcher claims to have found a drug that causes people to grow taller. The coach of the basketball team at Brandon University has expressed interest but demands evidence. Over 1,000 Brandon student volunteers to participate in an experiment to test this new drug. 50 of the volunteers are randomly selected. Their heights are measured and they are given the drug. 2 weeks later, their heights are measured again. The power of the test to detect the average increase in height of 1 inch could be increased by how? Now, what you want to keep in mind is, what does power mean? So if this is our hypothesis, we are assuming H sub O in this case is going to be, for example, measuring the mean. So if this is where the H sub O hypothesis is for the means. However, we really think it would have been over here. So based on our alpha, or what we used for our condition here, we can interpret the power. If we draw that down to where it would hit here, this area to the right on what we think the answer really would be in the blue curve, this is the amount of power that our test has to detect that this is really a better answer. The blue curve's a better answer than the red. So would it help using only volunteers from the basketball team in the experiment? Clearly, letter A is not a good option. Volunteers is not going to be random and is not going to be a good study at all. It breaks the rules from Chapter 4. Letter B, using a 0.01 instead of a 0.05 will actually increase the significance, which means if they are saying currently use 0.01 instead of 0.05, if this is 0.05 right now, okay, this is all of our power. Now, if we take this green line and we reduce it to 0.01, it's going to have to go to the right. Well, if we go over to the right down here, you're going to notice as we hit the blue curve, we've actually reduced our power. And what we want to do in this case is to increase the power. So no, this doesn't work for B. B actually reduces the power by reducing our alpha, or our significance. What if we went the other way? What if the scenario is we use 0.05 instead of 0.01? So assume this is 0.01 now. If this is 0.01, all this yellow space is our power. Well, to move to 0.05, the green line is going to go over here to the left. Well, that's going to give us more space here, and we're going to actually gain more power in this region. So letter C in itself actually does give us the power that we need. So knowing that increasing the significance level increases power, decreasing the significance level decreases power. Let's just talk about the last two, even though we know the right answer. D, giving the drug to 25 randomly selected students instead of 50. This is talking about the sample size. So if this curve, if you think about it, represents the sample size of 50 students, what if we only gave it to 25? If we did, this distribution would not be as stable. A sample size of 25 is less stable. It's a smaller sample size. So what you would see is you would see this graph actually spread out more in this direction and spread out more in this direction. As it spreads out more into the right-hand side, imagine this green line for the significance level actually pulls itself over. As this green line pulls itself over, it's going to cut out less of this yellow space. You're going to actually reduce your power. So that means lowering your sample size reduces power. Increasing sample size increases power. Thus, this one is actually not going to work for our case. And then the last one, using a two-sided test instead of a one-sided test will actually not change the power that you see over here. What you're going to have, the difference is this, is if you had a one-sided test, when you compute p-value, you get this tail. If you have a two-sided test, it's going to actually give you the same p-value for this tail, but it's going to have to be replicated on the other side. So the difference between this is a two-sided test will give you twice as much of a p-value, but the power is still going to stay the same because your alpha is going to stay in this spot, and you're still going to have this probability for at least one of the tails, and you can measure the power. So for this case, letter E is not going to be valid because of that reason. Number 7, a 95% confidence interval for a population mean mu is calculated to be 1.7 to 3.5. Assume that the conditions for performing inference are met. What conclusions can we draw for the test that H sub O is mu is equal to 2 versus H sub A was mu is not equal to 2 at the 5% significance level based on the confidence interval? The one connection to make from this problem is how the confidence level and the actual alpha of a test are related. So if you're doing a 95% confidence interval, but you would do a test using an alpha or significance level of 5%, those are going to be complements of each other. So in this case, this would be more of like the two-sided test. This is making up the 0.05%, or really our significance. So the confidence that goes along with it is a 95% confidence interval. So first of all, that's an interesting point to be made. Now our sample in this case came up with a confidence interval between 1.7 and 3.5. But if you look at the actual hypothesis, combining a test with it, the hypothesis was that H sub naught is that mu is equal to 2. Well, the problem is mu of 2 actually falls within this range. Because mu of the population does fall into this range, all you can really say is you have to fail to reject H sub O at that level. And it really is just letter E. Now, that's the right answer, but when would it be the case that letter D would work? When could you reject it? If, for example, let's say we thought the population mean was really the number 1.6. Well, since 1.6 does not fall into this range, if that was the case, then we could say we would reject H sub O and we could conclude H sub A. Letter C definitely does not hold. It says here confidence intervals and significant tests are not related. That is actually not true. Only a two-sided significance test and a confidence interval are related. It is true that one-sided significance tests and confidence intervals are not related. Part B is definitely wrong. A 5% significance level is not connected to a 75 or a 97.5% confidence interval. It is connected to a 95% confidence interval. Remember, these two values are complements of each other. And in this case, because they gave us the confidence interval, we know what the value was from the sample, and we know what the hypothesis was about the initial population. Letter A is not true. We don't need the original data. We have enough information to actually, in this case, not make a conclusion, because we would have to fail to reject H sub O, and then means we cannot conclude H sub A. Number 8, a test of H sub O is P is equal to 0.04. Against H sub A, P does not equal 0.04, so a two-sided test. A random sample of size 100 yields a test statistic of Z is 1.28. The p-value of the test would be approximately equal to what? So let's set up a scenario. Now, if you notice in my sketch, these are z-scores, so this is the z-score of 0. 1.28, because it's a two-sided test, we could go this side, but remember, we're also talking about the back end on this one too. It's really kind of mirror image on the other side. Well, all I would do is just come on in here and do a normal CDF, and you could do the lower bound and upper bound of maybe the right-hand side. I could go 1.28 to 999. Because this is the z-score, I would just do 0 and 1. Whatever we get for this value, I believe it's going to be 0.10227. Because we have to replicate this over to this side, just take it and times that by 2. And then that's going to give you the answer here, which is letter D. Number 9, an SRS of 100 postal employees found that the average time these employees had worked at the Postal Service was 7 years, with a standard deviation of 2 years. Do these data provide convincing evidence that the mean time of employment mu for the population of postal employees has changed from the value of 7.5? That was true 20 years ago. To determine this, we test the hypothesis that H sub O, mu is equal to 7.5, versus H sub A, mu is not equal to 7.5, using a one-sample t-test. What conclusion could we draw at the 5% significance level? Well, if you sketch out this scenario, one thing we are noticing, it's a two-sided test. So if we go ahead and look at that, we're going to be trying to find the p-value, which should be both of these tails. So if I can find one of the tails, I could just times that by 2 and get the actual p-value. Then what I'll do is compare the p-value to our alpha. So for this one, let's compute, it is the means. We do not know the population standard deviation, so this is going to be a t interval. So let's go ahead and compute the test statistic in this case, which is going to be t is equal to, it's x bar minus mu sub naught over S of x over the square root of n. So in this case, we do know that x bar is going to be our 7 minus our 7.5. Standard deviation is 2, and divide that over the square root of 100, which will end up being 10. Simplifying this gives us a t critical value of negative 2.5. So the negative 2.5 critical value is going to be right about here. And we want to find this probability. So what we can go now is we can do t CDF, because we want cumulative on that. And we're going to go lower bound is negative 999. Our upper bound is negative 2.5. And this one calls for the degrees of freedom, which is sample size minus 1. So let's put 99 in there. And when you do that, we're going to get 0.007. Because this is a two-sided test, we do need to take that value and actually times it by 2. So we're going to get 0.014 as our p-value. Now, based on that, our p-value is less than alpha. That is, 0.014 is less than 0.05. Because p is less than alpha, we can reject h sub o, and we can conclude h sub a. Based on that, there is convincing evidence. So if we look at our answers, we can cross off b, and we can cross off e. How would you make the conclusion then? Of the 3 that are left, all that we do know is that it has changed. We don't know by how much or compared to what. So the correct answer for our conclusion would be letter A. Number 10, are TV commercials louder than their surrounding programs? To find out, researchers collected data on 50 randomly selected commercials in a given week. With the television's volume at a fixed setting, they measured the maximum loudness of each commercial and the maximum loudness in the first 30 seconds of regular programming that followed. Assuming conditions for inference are met, the most appropriate method for answering this question of interest is what? Now, the best way to first think about this is proportions or is this means? What they're measuring here is the maximum loudness. Loudness itself would be like a volume in decibels, so it's not a proportion. So basically anything with one proportion could be crossed off. Is it a paired t-test or a paired t-interval? That's the question. Do they want to actually construct a confidence interval or do they want to do a test? Now, what they initially asked in this question, are TV commercials louder than their surrounding programs? They really want the answer to be yes or no. They didn't ask for the range of by how much are they different. If they had asked for a numerical range, like we could actually visually see in an interval, we would maybe do an interval. They, again, just want yes or no, so we are talking about a test in this case. Now let's double check. Would it be a paired test? It would make sense that they would do a matched pairs on this one. They would do the volume before or during the commercial and then the volume the 30 seconds later and compute the difference. So in this case, the paired t-test does make the best sense. Just for some more insight, it might be helpful to know what would they test. Well, h sub o, what they would test in this case is that the mean difference is actually equal to 0. But the true hypothesis is they really think the mean difference is going to be greater than 0. Again, depending on how we compute the difference. If we would say the difference is the commercial minus the TV show, we would say it's greater than. If we did the TV show minus the commercial, we would use less than instead for this case. So you would want to make sure you define mu sub d as commercial minus the show, because it's very important which direction we're looking at it to make sure h sub a would be stated properly. So number 11, a software company is trying to decide whether to produce an upgrade of one of its programs. Customers would have to pay $100 for the upgrade. For the upgrade to be profitable, the company needs to sell it to more than 20 of their customers. You may contact a random sample of 60 customers and find that 16 would be willing to pay $100 for the upgrade. A, do the sample data give good evidence that more than 20% of the company's customers are willing to purchase the upgrade? Carry out an appropriate test using a significance level of 5%. Now the first thing I'm going to do is think about state, plan, do, and conclude. So I'm going to do is state the hypothesis. So for this one, h sub o, we're going to say p is equal to 0.20 or 20%. That's our null hypothesis because we believe h sub a is the case that p is greater than 0.20. And I should define that P is the proportion of consumers willing to pay $100 for the upgrade. So do define the variable P somewhere. And we are using the significance level of 5% as they've already defined. And that's enough for state. Now in the plan part, let's talk about which test we're planning on doing. The AP board either wants you to write the formula for the test statistic or just name the test. I think it's easier to name it. This is going to be a, and I would get credit for just stating this right here. Now let's check our conditions of random, independence, and normalcy. So for randomness, all we need to confirm is that the sample is done randomly, and they do say that in the problem, but make sure you do write random sample was taken. For independence, let's test this one. Independence is the population greater than or equal to 10 times our sample size. Our sample size in this case was 60 people, so 600. And you would write, yes, we can assume there are at least 600 people to choose from for our customers, so therefore independent. See? What we're going to end up finding is that n was 60, p hat is 16 over 60. Therefore, in this case, what we have is we're going to see that 16 is greater than or equal to 10. And then the complement of that is going to be the 44 is greater than or equal to 10. Meets the requirement. Therefore, I am going to write that it is approximately normal. Don't just put regular normal because that's not correct. We'll just say approximately. And the conditions have been met. So now for the do part, if we do write this out, let's write out the test statistic for this one. So we are doing a z proportion. The z is our test statistic. And the formula for that is going to be p hat minus our p naught divided by the standard error of that, which is going to be p naught times 1 minus p naught over n. P naught is going to be 16 over 60, or I'm sorry, p hat is. P naught in this case is our 20%. And then if we put this into the formula for the standard error part, our p naught is 0.2, 1 minus 0.2 is 0.8, and that again is going to be over 60. This will end up getting us a z-score of 1.297. Now, the test is actually looking at, we want the proportion to be greater than that. So if you imagine us looking at this in terms of the normal curve, our standardized form here, we want to have the z-score to be at 1.297 and above. So let's just do a normal CDF. We're going to use normal CDF. We will use our lower bound of 1.297, upper bound of 999, and I'm going to do 0 and 1 because I've already standardized it. When we do that, we are going to get back a p-value for this of about 0.0968, and that is our do component. Now for the conclusion, let's go ahead and make our three specific points. First thing is we want to compare our p-value to alpha. In this case, p-value is greater than alpha, and I'm going to write that out. Because of that, I make the second component, which is that we failed to reject H sub O. And then you'd make your final conclusion. Because we failed to reject H sub O, we cannot conclude H sub A that the proportions are greater than 0.2. Never, ever conclude H sub O. That is one of the biggest mistakes people will make. And that's how you do Part A. Now for Part B, this particular question, which would be more of a serious mistake in this setting? A type 1 error or a type 2 error, and justify it. Now remember, a type 1 error says you reject H sub O and you conclude H sub A. Well, if we were to reject H sub O and conclude H sub A when it was an error, what that would have caused us to do is assume the proportion would be higher than 20%. Therefore, we would produce the upgrade, this upgrade. Well, in producing this upgrade, we would lose money because we didn't need to do it. Now, a type 2 error is we failed to reject H sub O, thus we do not conclude H sub A. Now, in this type 2 error, what that would cause us to do is, since we don't conclude H sub A, we wouldn't do anything. We would leave everything as it was. Well, if we leave everything as it was for this type 2 error, the consequence could be that we would lose some profit. So which is worse for us, the type 1 error or the type 2 error? In the type 2 error, remember, we would actually produce this upgrade. It would cost our company money. The type 1 upgrade or error, we wouldn't do anything, so we'd lose profit. In this case, this would have cost more money out of our pocket, so the type 1 error is more serious of a mistake. Now, letter C, other than increasing the sample size, describe one way to increase the power of a test. Increasing sample size is a great way to do it, but another great way to increase the power of a test that's really easy is just to go ahead and increase your alpha or your confidence level. Number 12, I can't get through my day without caffeine is a common statement for many students. Assumed benefits include keeping students awake during lectures and making them more alert for exams and tests. Students in a statistics class designed an experiment to measure memory retention with and without drinking a cup of caffeine or coffee 1 hour before a test. The experiment took on 2 different days in the same week, Monday and Wednesday. 10 students were used. Each student received no coffee or 1 cup of coffee 1 hour before the test on a particular day. The test consisted of a series of words flashed on a screen, after which the student had to write down as many of the words as possible. On the other day, each student received a different amount of coffee, none or 1 cup. Part A here. One of the researchers suggested that all the subjects in the experiment drink no coffee before Monday's test and 1 cup of coffee before Wednesday's test. Explain to the researcher why this is a bad idea and suggest a better method of deciding when each subject receives the 2 treatments. Now, this is a really good review question from Chapter 4. What you want to take away from here is that random assignment is actually very important. The random assignment actually allows us to control for lurking variables that may confound with the response variable. Some things to keep in mind for this experiment. Some students may improve from Monday to Wednesday just because they'd already done the 1 task on Monday, so you want to control for that lurking variable. Also, some external factors may affect the scores on the days. Perhaps the student didn't get as much sleep on Monday for Monday's test, but they got more sleep on Wednesday's test. So if you randomly assign it, you can control for it. A good way to probably run this experiment, the better suggestion, would be to randomly assign half of the students to get 1 cup of coffee on Monday, and then the other half to get 1 cup of coffee on the Wednesday. So it's adequately spread out. Now, Part B, the data from the experiment are provided in the table below. Set up and carry out a test to determine whether there's convincing evidence that drinking coffee improves memory. So again, we're going to do state, plan, do, and conclude. First thing we want to address is our hypothesis. When we write it, are we talking about means or proportions? In this case, we are talking about the performance on a test, so it would be the means. Now, we need to think about what type of experiment. We actually had, basically, it was a matched pairs experiment. So each student was the one subject given 2 different treatments. So for matched pairs, what we need to do is find the difference in the results for each student. So let's go ahead and do this and first define our hypothesis. I'm going to say H sub O is that we think the mean is equal to 0, but we really don't. Our alternative hypothesis is going to say we think the mean is greater than 0, or the mu, I should say. We need to define this, though, because it's important. It's going to be the 1 cup of coffee minus the no cup. Because if we did no cup minus 1 cup, we would expect the mu to be a negative answer. In this case, we are assuming, as our statement, it's positive. And let's go ahead and pick an alpha of 5% is a very good standard one. And our state is complete. Now, let's do the plan. For the plan, at this time, I am going to state what I'm going to do. We are going to perform a 1 sample. This is the mean, so it's going to be a t-test And this is for the difference of means. And then we're just going to go ahead and check our conditions. For our first condition in terms of randomness, there is, in this case, there was random selection made, so we are good on that. To check for independence, let's see if we have our sample size that we have chosen here. We can tell there's 10 students, so for independence, n is greater than or equal to, in this case, 100. And I would make the statement, yes, there are at least 100 students for me to choose from. For approximately normal, this is the means. So what we need to do is think of the central limit theorem. Unfortunately, our sample size is at 10, so we can't use the central limit theorem. What we do have to do is actually graph out this data and look at the results. So what you need to do is actually compute what the data is. The data in this case is going to be the difference. So I would come on in and compute the difference for here. We said 1 cup of coffee minus that, so it'll be a +1, a +1, a +1, a 0. Compute your differences. We have 2, 2, 0, 0, and 2. So the data we're actually going to use are the differences that were computed. If we sketch that, I think a really good way to sketch that difference, I'm thinking a dot plot would be just sufficient. So come on in here, do a quick dot plot. This is going to be of the differences. And it looks like we have from 0, 1, put right here, and then the 2's. And if we plot the dot plot, we're going to get this shape right here. Remember, we are under 15, so we have to be even more specific about the shape and no outliers. So less than 15, we need no outliers, and we have to say that there's little skewness. So I would actually make the statement there are no outliers in this case. There is little skewness, so therefore we can say approximately normal, and the conditions have been met. Now, for the do component, let's go ahead and actually get the information we need. You're going to have to go back to Chapter 1 concept. We're going to have to do a one variable stat to do our test statistic for this one. Remember, the test statistic for the do component is going to be x bar minus our mu sub naught over s sub x over the square root of n. We have to get x bar and s sub x actually from our calculator, so I'm going to put my data into list 1. I'm going to do a one variable statistic on that. When I do the one variable statistic, what I end up getting here is that we get that x bar is 1, s of x on the calculator is 0.816496. So if we put that data into our test statistic down here, we're going to have 1 minus our 0 over our standard deviation that we just calculated over the square root of 10. That's going to give us a test statistic of 3.87. Now, we do think it's going to be greater than, so what I would do for our probability calculation in this case, I'm going to go ahead and do a TCDF. We want to go from 3.87 to an upper bound of 999. This is based on degrees of freedom, so we have sample size minus 1. This will give us a p-value of 0.00189. And that's our do portion. We now can make our conclusion for this. So let's go ahead and do the conclusion for this one. And here we go, the 3 parts we need to address. In this case, p is going to be less than alpha. I'm going to show that calculation. 0.89 is less than 0.05. It's the first part. Therefore, we can reject h sub o is our next part. And we can conclude h sub a. So I'm going to say we can conclude that the mean difference, or the difference in 1 cup of coffee versus no cups of coffee does make a difference. And that's how you'd go about doing the test. Number 13, a government report says that the average amount of money spent per U.S. households per week on food is about $158. A random sample of 50 households in a small city is selected, and their weekly spending on food is recorded. The mini tab output below shows the results of requesting a confidence interval for the population mean of mu. An examination of the data reveals no outliers. Explain why the normal condition is met in this case. So in here we are looking at a sample size of 50. Clearly on this one we have met the central limit theorem that n is greater than or equal to 30. That is 50 is greater than or equal to 30. Therefore we can say approximately normal. Be careful, the normal condition. Sometimes people will intertwine that with the independence. To test for independence, remember, is just going to be capital N greater than or equal to 10 times the sample size, where capital N is the population. Showing independence allows us to actually compute a new standard deviation. Part B, can you conclude that the mean weekly spending on food in this city differs from the national figure of $158? Give appropriate evidence to support your answer. Now, the first thing I like to do is actually imagine what the hypothesis was. So is it different from 158? Therefore, H sub O was assuming that mu was 158. Is it different would be a two-sided hypothesis. So that mu is different from 158 is what they conducted here. Remember, a two-sided hypothesis can also be compared with a confidence interval. We can get that information. I would assume possibly they used an alpha. We could use an alpha of 0.05 for this case. So looking at this information, here's the confidence interval for that. All you need to do is if they've done the test, you're fine and you can look at it. We don't have any computer output about this particular hypothesis test. We don't need it. Because this hypothesis test is two-sided, we can also look at the confidence interval to get the information. So in this confidence interval, you're just trying to see is the population assumption of 158 within the interval. 158, our null hypothesis, is not in the interval. Because of that, we can reject H sub O, and we can conclude H sub A. Now, what is H sub A? What I would say, because we need to put H sub A in context, we would say that the spending for the households is going to be different than $158. So when you have a two-sided test, you just need to recognize there's multiple ways you can actually answer that test, which is kind of a nice connection.